The Bernty principle. Here used in the Bernty pump as a sample. A better way to accumulate and use wave power. After numerous designs of a device that could catch the power of a wave, I finally got something that worked. In this example I will use a pump to describe the principle, but obviously the technique works equal well for other than a pump. Granted, the standard solution, a piston operating on a float, kind of works but far from well, especially in smaller waves. The problem is this: at least working with rather small lake waves or coastal waves, the front and crest of a wave is rather short both in length as well as time compared to the trough of the wave. In that time the float has to accelerate not only the mass of the float and the mechanics of the pump, piston rod, couplings and so on, but even worse, the water in the system. Any height of the outgoing water head will hydraulically act on the piston at 1 pound per square inch of pressure for each 2.31 feet of head. That, in addition to the general friction, both of the water as well as the mechanics, makes it very hard to get a direct float/piston system to work. With that in mind, I concluded that the float must operate on as little mass as possible. So here is my solution. Rather than operating a piston that directly pumps the water, the float only pull on a lightweight hollow rod, red, inside a larger pipe, and connected to a spring. At the crest of a wave, the float pulls the rod up, that in turn creates a vacuum inside the housing, sucking in water via the left check valve. At the same time it tightening/stretching a spring, and when the float goes into the trough of the wave, this rod will be pulled down by elastic energy, stored in the spring. That causes a displacement inside the pump housing, forcing the water out via the check valve on the right. Yes, it could be a piston with O-rings, but I found that just a rod, with no contact to the sides of the pump housing, works better and has less friction, not to mention easier to make. The same principle as if we fill a bottle full of water and stick your finger into it. The finger will displace the water, and the bottle will overflow. The other advantage of this system is that the outgoing water pressure will always be according to the force of the spring, in relation to the square area of the rod. For example, in my prototype, I used a 1/1/16 PVC rod inside a 1/2 inch PVC pipe. 1/1/16 inch is close to 1 inch too, and I used a 15-pound spring. That gave me about 15 pounds per square inch of pressure, and more than 30 feet of head, calculated. The float can be just about anything. The lighter the better. I was using a 24-inch inflatable hopper ball for my experiment. However, I think the ideal shape would be an elliptical sphere. Also, ideally, there should be a tension on the float, so at the wave's rest level, the spring should be stretched at about 50% of the spring's working limit, so the total travel for the spring, between the crest of the wave and the trough of the wave, would be about 100% of the spring's workable stretch. I could see a simpler version of this pump, using a rubber bellow with the spring incorporated in the rubber. That would make it a sealed system, able to pump any liquid, not necessary the medium the pump is submerged in. Same here, the lift from the float would compress the spring/bellow, creating suction in the housing, filling the housing with water via the green gate valve on the left, while in the trough of the wave, the spring would expand, creating a displacement forcing the water out via the red gate valve on the right. Realizing the capacity water has in regards to lift, converting to elastic force, this system could obviously be used for other than pumping a liquid. Depending on the size of the float, and the shape of a float, we could gain movement larger than just the height of the wave. As an example, if we sit in the back of a rowboat and look at the front of the boat, we can see that it moves up and down considerable more than the height of the wave. A way to extend the stroke of the movement without gearing. This lifting force can then be accumulated in a spring, bungee cord, gas spring or whatever that can hold an elastic energy, to be released in a controlled way for whatever the need, like electrical generation, mechanical force, pumps or whatever. In an ocean, there should be no need to extend the stroke, so a simple float to spring connection should suffice. Here we can see that after priming the pump, a pull on the rod stretches the spring inside the housing, that in turn forces the rod down when let go, forcing the water out via the hose. Sample of an ocean beach setup to generate power.